Okay, good morning, good afternoon, everyone. Welcome to this webinar about smart NVH design of electric vehicles powertrain. My name is Romain Botson. I'm the Actran product marketing manager. I'm very pleased to be here today virtually with Mustafa Douyar, the FEV product manager that will present today together with me. This is the agenda of today. So in the first time, well, we will understand together what are the current background of the electric vehicle market and understand together why we observe basically a growth in this market. We'll then, of course, understand what are the related NVH challenges and in particular the ones that we have to deal with when it comes to powertrain designs. Well, having understood these challenges, we will present you the solution we have for smart NVH design of electric vehicle powertrain, and in particular the new virtual dynamics capabilities, offering combined electromechanical, dynamic, and acoustic prediction. We will review different case studies and applications and conclude before opening the Q&A session. So during this webinar, well, if you have any question, please type them in the dedicated Q&A area, and we will answer them at the end of this webinar. So let's start. Let's review together what's happening on the automotive market, what's the context, and the different challenges. Well, actually, everything is related to emissions regulations. And all major automotive markets in the world do have emissions regulation in place. These regulations are diverse depending on the countries, but all aim at reducing the emissions of CO2 and improve fuel economy. Well, if we have a closer look at the European CO2 emission, well, in 2020, we will have the entrance of a new CO2 emission target that will be joined by an excess emission premium for manufacturers failing to meet these targets. So looking at, well, the current emissions performances, well, the 2020 regulation is actually asking a 27% emissions reduction to all OEMs, and therefore pushing powertrain engineering to limits. And this is why, well, in order to achieve this reduction, well, electrification is actually needed. Now, if we look at the offer of electric vehicle on the market, well, we can see the impact of those regulation on the number of models that are offered by different OEM. And in particular, since 2010, we can see an increase of the offer by all different OEMs. Now, behind this offer, well, there are different engine technologies from hybrid electric vehicle, plug-in hybrid electric vehicles, BEV or battery electric vehicles, or even fuel cell vehicle. But according to the projections, it will be the plug-in hybrid vehicle or plug-in or hybrid electric vehicle and BEV that will be dominant technologies in the coming years. Now, let's understand together what are the NVH impact and challenges related to this increase of electric vehicles. So we know that engineers will have to develop new engines design and new engine technologies. And we have seen previously that one of the new architecture that will arrive on the market is the hybrid engine architecture, which means that we will have to deal with new driveline connections, potential issues related to non-continuous torque. On the other side, um, we will see the introduction of electric vehicle architecture, so pure electric vehicle architecture. And related to these architectures, well, we will have to cope with low and also high frequency challenges. Strongly related to that is the fact that now, because we will somehow reduce the noise emitted by classical thermal engine or internal combustion engine, well, the remaining noise sources will become dominant. And when we talk about those sources, well, it will be the interior HVAC noise sources. Road and tire noise sources will also become dominant. And last but not least, wind noise related issue might appear. But in addition to that, OEMs will have to also work on lighter structure in order also to cope with fuel consumption reduction. And we all know that EV vehicles are also perceived as high-tech technology, increasing passengers' sound quality expectation. So these are all the challenges we will have to cope with as engineers. And today we'd like to focus on new engine design and how to cope with them. Now, if we look at the different engine design that will arrive on the market, so we know that we will mainly hybrid electric vehicle and pure electric vehicles. And what is common in between those different engine design or engine architecture is that we will have, of course, an electric motor. So it will be important to understand how this electric motor is behaving, so how the electromagnetic forces are inducing vibration on the stator, and how those vibrations can impact the NVH performances of the vehicle. On the other hand, we know that we will have reducer or gearbox as well. And those systems are actually complex systems involving numerous components. So we need to better understand how these components are acting together. So what do we have in our hands? What are the tools we can use in order to understand how electric motors are behaving and how they are connected to reducer gearboxes and how this complete system is performing? Well, we we want to present you our solution that is designed to make better NVH design through simulation. So we do offer a complete end-to-end solution from electromechanical load prediction to noise and vibration assessment. How is it done? Well, first we will have the multi-body simulation with virtual dynamics that will provide you with the structural loads when the powertrain and the engine is operating. Those loads will induce vibration that we will predict. And finally, well, those vibrations will be used to perform a noise radiation with Actran with high accuracy and in a very flexible and automated process. What is interesting is that actually electromagnetic simulation results from various software could be used in this process and easily integrated when it comes to electric motor noise prediction. So now it's time for me to give the hand to Mustafa Douya, who will introduce you to virtual dynamics.
So thank you, Roman, once again for the introduction, and thank you all for joining us today. So during the rest of this webinar, I'm going to talk about a seamless integration of the simulation toolset, which are Atoms, Actran, and Virtual Dynamics for smart NVH design of electric vehicle powertrains. What is Virtual Dynamics? How it was born? I'll start with this. So Virtual Dynamics used to be called Adams Engine, and it was developed with tight collaboration and strategic partnership between FEV and MSC Software. FEV put its powertrain and mobility solution expertise, and MSC Software put its simulation software development expertise, by which Adams Engine was born. And the first release was back in 1998. And back in 2008, it was rebranded as Virtual Engine. FEV continuously expanded its fields of application to gearboxes, transmissions, drivelines, and e-mobility, and eventually we rebranded it to Virtual Dynamics. So it has a solid background. Virtual Dynamics technology is based on atoms. On top of that, we first create a template-based architecture, which ensures modularity, incremental fidelity levels, reusability, and quality assurance of the models. Then we also provide powertrain and driveline specific modeling and analysis and result sets. In other words, predefined powertrain and driveline modeling elements and simulation results that significantly increases the efficiency of the simulation-driven product development. So this slide summarizes the typical fields of application of virtual dynamics. So the history was, as I said, it was Adams engine, then virtual engine. So we still support modeling and simulation of conventional engines, internal combustion engines, and it is subsystems, including valve train, timing drive, crank train, including bearings, piston group, connecting rod, including VCR connecting rod, turbochargers. So as for the driveline, we address transmission, test bench, entire vehicle driveline simulation. And we also, of course, address e-mobility with the modeling and simulation capabilities of electric motor generator, hybrid power packs, range extenders, and belt starter generator systems for the hybrid electric vehicles. So after this, a little bit of history and virtual dynamics. First connection to MSC software. We will now first talk about powertrain NVH, and then we will talk about 3 different use cases where we apply this methodology. So to predict the powertrain structural bore noise, we first need the calculation of mechanical excitations. For this, we carry out multibody dynamics simulation with flexible components of powertrain, no matter it is conventional IC engine, electrified powertrain, or pure electric powertrain. We calculate the structural vibrations. They are in form of displacements, velocity, or accelerations. By using these predicted surface vibrations, we then use Actran to calculate the acoustic radiation. So now if we look at the simulation process, so as I said, we first do multibody dynamics simulation with the flexible bodies in virtual dynamics. So in most of the cases, we use Actran to calculate the structural modes, which is fed onto virtual dynamics model at flexible bodies. And we run virtual dynamics simulation, which creates participation factors. Then both structural modes and participation factors can be passed to Actran for acoustic radiation calculation. So this is a traditional way to do this. So in this scenario, you would need really an acoustic expertise. So what we have done recently is we eased this process. So we introduced so-called Adams to Actran plugin. So directly within virtual dynamics environment, we can launch acoustic simulation. Behind the scenes, Actran solver runs and creates the acoustic results. So if I try to point out a couple of highlights about the main features of Adams to Actran plugin. So it is based on finite element method, the acoustic calculation. It can either do transient or frequency domain solution. It is fully integrated within the virtual dynamics graphical interface. So it really provides fast acoustic results thanks to Actran features, and it provides acoustic indicators including sound pressure levels, sound power levels, uh, frequency analysis. We can even generate audio files that we can listen to noise. And we also have full capability of extending Actran features for advanced modeling. So once we complete the virtual dynamic simulation with flexible housing for the acoustic analysis setup, we have eigen modes and by means of MNF file and model responses, in other words, participation factors by means of MDF file. So by using these two files, we can do Actran time domain simulation and generate time domain results. And afterwards, we can apply Fourier transformation, get the results in frequency domain. So alternatively, it's also possible to carry out the Fourier transformation directly to MDF file, participation factors. So we get the participation factors in frequency domain, and then we can run Actran simulation in frequency domain and get the results faster when compared to time domain simulation. So a little words about acoustic solver. So we start with the structural mesh. The model on the left-hand side shows the structural mesh of the housing, and the structural mesh participation factors and the simulation parameters are passed to acoustic solver, and acoustic mesh is generated automatically, which is optimized for the frequency range of interest we have. Actran solver calculates acoustic pressure at microphone locations, and results are exported in the output folder with picture formats that you can easily take a look later on. So after this process introduction, let's take a look at 3 use cases, starting with the engine radiated noise, which was carried out by Ford. And this is actually an internal combustion engine, but this process is well established at our customers, including Ford. So it really generates very good results and improvement of NVH. It was presented at our virtual development symposium last March in the US. So it is even possible to listen the engine noise that I'm going to run now. So we start with the virtual dynamics model on the left, which is a 3-cylinder engine, and then we predict the surface velocities of the engine structure in virtual dynamics, which is then passed over to Actran for acoustic analysis. That generates many acoustic results, including audio file. And this methodology was used at Ford to improve the engine noise. So there are 3 different engines, A, B, and C. So I'll just show you, I'll just get you listened the engine A first, which has a gear whine noise. And then after applying this process, engine C actually doesn't have any gear whine noise that you can listen. So it was really quiet engine. That's why maybe you couldn't hear the engine C noise. Okay, so it was really a quiet engine. That's why you couldn't hear possibly. So now if we look at the P2 topology hybrid powertrain use case, so we have an inline four-cylinder engine coupled to a manual transmission that was also coupled to an electric motor that you can see as a red cylinder. So this model consists of flexible housing, flexible shafts, 3D analytical gears, IC engine, dual mass flywheel, the gearbox oil type, and the operating temperature. So at this point, I would like to give you some insights about the e-motor features within Virtual Dynamics. So it is a three-dimensional e-motor element with a shaft or hub drive options. It can be fully parametric, or it can be a flexible electric motor to study NVH and drivability. So we take into account periodical, tangential, and radial forces, and the electromagnetic results are imported from commercially available electromagnetic software. The main purpose of this e-motor element within Virtual Dynamics is to study dynamics of hybrid and electric powertrain topologies. So hybrid powertrain topologies are classified from P0 to P4 that you can see in this picture here. So the schematic picture explains this. Depending on where electric motor is mounted, these red boxes here, we classify the hybrid topology from P0 to P4. On the top, you can see different topology virtual dynamics models. So within the scope of this webinar, we will not talk about or show any use cases for P0 or P1 topology, but we will focus on P2 topology and pure electromechanical powertrain. If we go back to a virtual dynamics model, we have an accelerometer mounted on the flexible transmission casing that we predict the acceleration. This is a virtual accelerometer. And on the test bench, we also measure the acceleration exactly at the same location with an accelerometer. And we compare the results of this simulation. On the left, you can see the measurement, and on the right, virtual dynamics prediction for the acceleration. So very left-hand side is the microphone measurement, then accelerometer measurement, and the acceleration prediction by virtual dynamics. As you can see, we were managed to match both amplitude of accelerations as well as the main order of the excitation, the frequencies. So it was a very good correlation. It was only possible because virtual dynamics can couple engine, transmission, and electric motor all together and carries out a fully coupled simulation so that we can see all the effects of this system interaction. So afterwards, if we move to electromechanical powertrain example that is used in battery electric vehicles. So this is electromechanical powertrain, which consists of an electric motor and a two-speed automatic gearbox. This is the virtual dynamics model on the left-hand side, and you can see the schematic view of this model on the right-hand side. So this model consists of flexible electric motor housing, as well as flexible gearbox housing, flexible gearbox shafts, radial and tangential electromagnetic forces for each stator tooth are imported from electromagnetic software. The speed of this gearbox is controlled via this revenue planetary gear set, depending on which planetary gear sets carries out the power flow. We can decide which speed is transferred to the output shaft. So we also have detailed roller bearing models in the gearbox, as well as detailed gear tooth contact. So if I now move to the model setup, how this model is set up using our gear train wizard. This is a short demonstration. We launch a gear train wizard, and then we point to the property file of this wizard, on which we have 12 shafts, their locations, their length, what are the gears located each shaft, what are their properties, then what are the gear pairs and their properties, including detailed microgeometry modifications that you can see on the message window on the right hand side. Then once we press the build, the model is built automatically with the help of this gear train wizard. So after this, it is possible to change the fidelity levels of each component, including introducing the flexible bodies of shafts, transmission casing, as well as the gears. So afterwards, this is about some electric motor features. It is a radial flux electric motor, which has a maximum torque of 160 Newton meters. There are 60 stator teeth and 3 rotor poles. There are 2 different types that we can use, 2 different types of electric motor that we can use in virtual dynamics. Either it is a simplified one that we take into account only the torque, or the detailed one. The torque and individual tooth forces are taken into account that you can see on this plot here. So if we try to elaborate a little bit of the differences between simplified and detailed electric motor, with the simplified one, we miss the high frequency content if we look at the bearing forces that you can see on these plots. So after that, if we look at the results of virtual dynamic simulation at different gear sets, this is a speed ramp-up simulation starting from 3500 to 7500 RPM, and this speed ramp-up is happening in 2 seconds. So the gear pair contact forces of the revenue gear drive can be seen here between different planets and sun and ring. So the excitation due to e-motor is visible, as well as there is a potential of gear rattling because the forces changes sign slightly at this RPMs. So after that, if we move to the Addons to Actran plugin, how we set up the acoustic simulation within virtual dynamics environment. So now we are doing a frequency domain analysis. We select which flexible body to use to radiate acoustic results. Then output file prefix, the analysis name, MDF file name, the output start time is set in the units of seconds, and the end time is as well set. We can skip some of the steps between outputs. Now we define some analysis parameters, then the mesh. The PDF file is already provided, therefore we are selecting the PDF file. Then the result content can be selected, either just SPL or SPL in dBA. The analysis parameters then set, we can apply different filtering for the Fourier transformation. Then we define the frequency range, both start and end, as well as the step in between those and beginning and end frequencies. And yeah, we can use the adaptive volume mesh or hexahedral mesh. Then we set up the environment, which is air for this particular case. Then some setups with the far field. We can show the microphones that we are predicting or generating the acoustic results. And then finally, we set up the analysis, including the memory settings, and then we press OK, and Actran solver runs behind the scenes and creates the results. Now we can take a look at the simulation results. This is an acoustic analysis result. What we see here is the microphone 40 acoustic radiation. This is showing the main excited orders in the units of dBA. There are some low order resonances below 1500 Hertz, a group of higher orders which would generate high pitch sound, and this is what you normally expect from an electric motor. To understand the sources of the noise, let's go back to virtual dynamics model and evaluate the different force and torque inputs. Of course, all our input signals are in virtual dynamics in the time domain, so we perform a Fourier transformation to this time signal, and then we get electric motor rotor torque orders that we plot on this Campbell diagram. So these are the main orders of electric motor rotor torque. In the same manner, if we perform a Fourier transformation to the radial force acting on the stator tooth, this is the time domain signal, the forces, and if we apply Fourier transformation, we see the orders in the lower frequency range for the single radial force. Afterwards, we have a 60 teeth and 3-pole e-motor. That is, 3 equally spaced rotor teeth are always simultaneously loaded identically. And if we add all the radial forces in our e-motor and add them together, we get the curve on the right, and the Fourier transformation of this curve shows 2 dominant orders in the high frequency range that you can see here. So now, if we take all these orders and place them on our acoustic result, we can easily see that the radial forces are main contributors to the acoustic radiation and only small effects of the torque. The torque excitations would significantly impact the gear drive behavior. The noise, which we see here at around 1000 Hertz at very low speed, and this is due to potential gear rattling that we identified in the gear contact forces. So as we already saw, the radial forces are the main contributors to the acoustic radiation. So it is no surprise that eigenmodes of the hollow cylinder of the e-motor, on which the radial forces directly act, are the major eigenmodes contributing to the electric powertrain noise. So these plots show the eigenmodes and the major eigenmodes that contribute to the acoustic radiation. Finally, we can look at the element contribution over frequency range for different microphones. Here in this animation, you can see the microphone 57th contribution. And also we can listen which acoustic result is at this microphone as a wave file. Okay, so if I try to summarize, virtual dynamics is a vertical application based on atoms. Atoms to Actran interface integrated in virtual dynamics gives access to high accuracy acoustic predictions. Users with limited knowledge of acoustic simulation can now quickly and easily predict powertrain radiated noise. This capability helps engineers to improve the NVH performance of powertrains, and also users can push further the acoustic radiation analysis with the full capabilities of Actran, free field radiation, sound pressure level, radiation efficiency results, and study absorption mechanisms with the directivity plots, and even look at the complex propagation like pass-bias noise or absorption on floor, or rigid or porous structures can be studied. So before I thank all of you, I would like to announce two things. One is next week on Thursday, we have another webinar that we released the Virtual Dynamics 29. We will have this What's New webinar that you can see the details and the time here. So you can contact me if you're interested in this webinar. I'll provide the contact details later on. Second is on the 26th of November in Stuttgart, we are holding FEV simulation and calibration symposium. There will be a separate session for simulation in which virtual dynamics users as well as ourselves at FEV will share our experiences with virtual dynamics. So thank you once again for your participation and attendance.